Given the importance of predation, ecologists have spent a lot of time trying to understand it. So since Latka, we've been using mathematical models to understand the dynamical consequences of predation on interacting populations. We've learned that the demographic consequences of predation extend beyond just the species that predators directly interact with and can cascade through food webs. And then beyond just the act of predation itself, removing one prey from the population, just the mere presence of predators can induce profound behavioral changes in their prey that shape where they forage, how they move, their physiology, their morphology, which in turn feed back and affect population dynamics. But for all that we've learned about the consequences of predation, we still actually know surprisingly little about the mechanics of predation. And by mechanics, I essentially mean how does a prey evade a predator? How does a predator go about constructing an interception trajectory? And how do the traits of both predator and prey determine the probability that the outcome ends in capture versus escape? And this lack of a mechanistic understanding of the act of predation itself, I think, is holding back progress in evolution and in ecology. In evolution, we typically want to think about how does natural selection shape the traits of individuals in natural populations. In the context of predation, if we don't have a mechanistic understanding of the mechanics of predation, it's difficult to predict actually what traits natural selection should most strongly act on. And in the same time, for ecology, the ability to capture your prey is this ultimate bottleneck, which determines whether two species in a food web will be linked through a trophic interaction. And beyond just influencing the structure of these food webs, who eats who, it also can influence the magnitude of energetic or material fluxes across a food web due to variation in capture success, which varies, there's huge variation empirically across various predator-prey pairs from nearly 100% to almost 0%. So multi-order of magnitude effect of capture success on the rate of interactions between predator-prey pairs. Yet it's somewhat surprising, so given its importance for evolution and ecology, I find it somewhat surprising that we lack a general theory of predator-prey interactions, in part because the underlying principles are more or less conserved across various predator-prey pairs. So regardless of whether you're a dragonfly chasing a fly or a cheetah chasing a gazelle, the fundamental, to capture your prey, you have to get in close proximity. And prey can likewise avoid capture by avoiding the predator coming in proximity close enough to capture it. So it seems like from these basic principles, we should be able to generate simple models of predator-prey interactions and also compare the dynamics of predator-prey interactions across predator-prey pairs that vary in traits and how they move and respond to each other. Part of this limitation, so I think part of the reason why this hasn't been addressed yet, is a lack of high-resolution data on the dynamics of predators and prey as they interact, but recent advances in computer vision now allow us to track individuals as they implement natural behaviors such as predation and escape, reconstruct key sensory inputs like the relative orientation of the prey, and as well as motor outputs. So in this talk, I'd like to describe some of the work we've done over the last few years towards developing this general testable theory of predator-prey interactions with two main goals. One is understanding how traits relate to outcomes. So how does the traits of predator and prey, such as their speed or maneuverability, influence the probability that an encounter between a predator and prey results in capture? And secondly, to identify general principles or rules or algorithms that predators and prey should use to guide their behavior during interactions. So to begin with, while there's been relatively little general theory in the context of the mechanics of predator-prey interactions, the work that has been done has viewed predator-prey interactions purely as a biomechanical arms race between predator and prey. So that you've probably even heard this term, biomechanical arms race. The idea that evolution is generating this arms race where predators need to become faster to capture their prey, which also selects for prey to become faster to evade their prey. Well, empirically, predators tend to be faster than their prey. On average, predators are faster than their prey, and the vast majority of predators are faster. Can you evade a predator that's faster than you, which led to the idea that perhaps slower prey are able to evade faster predators through a maneuverability advantage. Perhaps they can turn faster than their faster prey and outmaneuver their prey or predators to avoid capture. And this kind of conceptual model of escape was formalized by Howard Howland in 1974 in this really influential paper referred to as the turning gambit. And the basic idea is it tries to encapsulate this trade-off between speed and maneuverability in this geometrical model. And the idea is that predators and prey have two traits: their speed and their maneuverability, which is captured by the minimum turning radius that they can make. So how sharply they can turn. And so here we have a predator that moves along its minimum turning radius with a given speed. We also have the prey, which moves along its minimum turning radius at a given speed. And the idea is, in the turning gambit, is that if prey are sufficiently fast and maneuverable, they can outflank their predator and essentially reach a zone that's biomechanically infeasible or unreachable by the predator due to limitations in its own turning ability. And the nice thing about this model is it's very simple and reduces down to this simple condition that prey can outmaneuver their predators when their scaled velocity or relative velocity, that is the speed of the prey versus over the speed of the predator, is greater than the square root of their relative turn radius.
So what is the model? That's the model? Or?
This is a prediction of the model. The actual model, it just involves solving for when these two lines intersect, and if the prey is able to reach this safe zone before the predator reaches the predator, then they can evade. The output, like one solution to this model, is this condition: prey are able to reach the safe zone if this scale velocity is
greater.
greater.
I was just asking what were the equations for the curves, I suppose. Yeah, but I guess you didn't write them down.
No.
And the safe zone means somewhere like a cave, somewhere hidden.
No, that's good question. So it's not actually. The safe zone is only safe because the predator is limited by its own turning ability. So if this is the minimum turn radius of the prey, then it can't reach this area, at least in the very recent future, because of its own turning limitation. So essentially, you're
turn back later.
They turn back later, but at this wider turn radius because of their relatively lower maneuverability.
So these curves are just circles?
Yeah.
Right. Explain.
Yes.
I'm also slightly confused about the meaning of turn radius, because if you look at this typical video, a dog chasing a rabbit, the rabbit is doing these very sharp turns. It's not that the rabbit is going in a shorter circle than the dog is. It's like this really intermittent straight line.
So typically this curve is probably better capturing the turning at the moment of turning, and then often you see that they break out of this minimum turn radius turn and go a particular direction. So in a little bit, and later on in the talk, we'll talk about models that kind of go beyond this extreme simplification and actually have the prey moving out in a different direction. But if you do look at many escape trajectories of prey, they often look something like a minimum turn radius turn, at least for a short moment right during the maneuver. Yes.
Is there a variation of this for 3D space? I'm just wondering whether it's in water or in air. This would be very different.
So this model actually wouldn't give you a different, because this is only based on the maximum turning abilities of the predator. It would result in the same predictions in 3D versus 2D, assuming that the constraints are symmetrical in all directions.
So probably not, that's why.
Yeah.
But in 3D, what if the trajectories aren't coplanar? If the predator tries to, let's say, take a different great circle around the sphere to the predator?
Yeah, then you might get a different, slightly different prediction. So this is all in 2D. And at the very end of the talk, we actually get to real evasive maneuvers by prey. They mostly fall on a 2D plane.
The turn radius itself, it does not depend on the speed. I imagine maybe you go.
It depends on how you move, actually. So for animals that fly and animals that swim, it tends to be independent of speed. But for animals that run, it does depend on speed. So the nice thing about this is it's a relatively simple model that depends on these biomechanical traits. And importantly, if we look at predator-prey pairs across different domains, so animals that fly or swim or run, these traits vary substantially, both due to variation in size, but also variation in the medium through which you move. So if this view is correct, if predator-prey interactions are really just comparing relative biomechanical traits, then we should be able to predict variation in the outcome of predator-prey interactions based on where a given predator-prey pairs fall compared to this v equals the square root of r. Yes.
But your example on the left,
yes,
the schooling,
yeah,
that's a totally different strategy.
That is. Yeah, it's hard to find a good. I guess I could have used one of our pictures. So yeah, that's right. That's a totally different picture. It's hard to find a good picture of pursuit predation for aquatic prey, but I could have used one of ours.
Is there a sense in which pursuit predation is like the dominant? Strategy out of all the possible
pursuit predation? Yeah, I would love to do. I've had conversations with ChatGPT about this because I want to know. It's like one of those things that it would be a ton of work to figure out and hard to find a good way. The one thing I thought of is just like randomly picking species off a list and then checking. But obviously the species that we have lots of information about are also a non-random sample. But I think probably ambush predation is slightly dominant strategy, but pursuit predation is not rare.
Sorry, just for us that do not know anything about that, what is pursuit predation?
So pursuit predation, in my definition, the distinction, so there's ambush predation, which typically implies that the prey is unaware of the predator, except maybe till the last moment. In pursuit predation, the predator is actively fleeing from the predator is chasing. And so the way that I distinguish them is whether there's mutual feedback between the behavior of the predator and prey on each other. So in ambush predation, the prey generally is not responding to the predator.
What about group predation or lions?
Group predation, it depends on that. It can be pursuit or ambush predation. I would imagine it's typically ambush. And then you have are the predators coordinating? Are the prey coordinating? We'll have one tiny example of some group predation at the end that we'll cover. But for the most part here, I'm just talking about one predator chasing one prey. So this is work done by Lars Koopmans, who's here, where we wanted to test this hypothesis that predator-prey interactions are basically just a biomechanical arms race. And if they are, and the assumptions of the turning gambit are valid, then we should be able to predict variation in capture success with how far you are from this v equals the square root of r boundary, where pursuit is an even match according to the turning gambit. So fortunately for us, there's been a lot of recent studies that have compiled extensive databases on important traits for this model. So for the first trait is the maximum velocity or speed of the predator and prey. There was this recent paper by Hurt where they compiled speed data as a function of size for animals that fly, run, or swim. All three show this kind of hump-shaped relationship where at the at small sizes, you get something that looks like a power law until eventually you reach a large enough size and the increase in speed with increasing mass begins to slow down and eventually reverse. So typically the fastest animals in any domain tend to be of intermediate sizes. The other thing you see in this plot is that flying animals are the fastest, then running animals, and then fish are the slowest. Fish have to move through a really dense medium, which makes them slower.
This cannot be extended to reptiles, no?
What's that?
They are very slow. Reptiles will not. fit
Reptile? I think, yeah, I don't know if reptiles are in this or not.
Komodo dragons can run very fast and they are large, so I think there should be some Komodo dragon.
Yeah, and then with reptiles too, then you have the problem of what temperature did you measure their speed at, because that's also going to be important.
That's also.
There are some fast snakes.
Okay.
I don't want to strike them. Just curious.
And so then the other trait is this minimum turn radius. There's less data available for this, but we can work out what these scalings for minimum turn radius should be across these domains. So essentially, to turn sharply, an animal needs to generate sufficient centripetal force to counter its inertia to cause it to turn. Terrestrial animals do this by pushing off the ground. All but the very largest animals, terrestrial animals, tend to be in a friction limited regime, where eventually if the turn radius is too small, their feet slip and they're unable to execute the turn. And then in the aerial and aquatic domain, it's essentially, they're both limited by the resistance from the medium through which they move, but there's one big difference, is that water, because it's 1,000 times denser, essentially pushes back much harder when animals turn, allowing them to make much sharper turns. And so Lars used a relatively simple model of uniform circular motion to calculate the forces available for the centripetal forces available in each of these domains, to calculate scalings for the turning radius across these three domains and as a function of body size. So these lines are the predictions from Lars's model, and the data points are observed turning radii that have been measured experimentally. Importantly, these lines weren't fitted to the data. The actual parameters for these scaling relationships were determined with independent data for things like lift force or drag force or the density of water, et cetera.
And these plots are the same species or different species?
These are different species. Yeah, so these are species that vary substantially in body size, and you see the same scaling in aerial and aquatic, but this almost 3 order of magnitude difference is almost entirely due to the differences in the density of water. And you see a different scaling, see this hump shape scaling for terrestrial animals, because it turns out that the scaling for the minimum turning radius is proportional to, I think, 1 over velocity squared. Okay, so we have models now that equations that give us predictions for the speed and turning radius. We also have data sets on predator-prey body sizes in each of these domains. And so we can sample random predator-prey body sizes, calculate the relative velocities and the relative turning radii, and then see where predator-prey pairs in different domains fall on this line. So if v over the square root of r is 1, then we're in this even match domain where small differences in the speed of predators or prey will shift the balance towards one or the other. If this value is much less than 1, it gives predators the advantage, and theoretically prey should not be able to outmaneuver. If it's greater than 1, prey should be able to outmaneuver. So prey have the advantage.
Sorry, one more question.
Yes.
Is there an implicit assumption that you're looking at pairs that are somehow, I don't know, balanced? So like you're not looking at a bird attacking an insect or something, or would that also fall in this?
We're looking, so the assumptions of this model, I don't know if we have in the predator prey data set, if there's examples of birds attacking like moth, for example.
Right.
But essentially we're assuming that they all follow this same scaling relationship, so we can count so that the relative velocities and turn radii that we calculate are valid. But there can be species-specific variation in these too. These are like the expected traits given their body size.
So in principle, it might work for insects.
Yeah, in principle, we haven't. So I think most of this analysis is focused on vertebrates. So we're actually whether we're kind of uncertain at the moment the extent to which these models are valid for flying animals, especially our assumption about the minimum turning radii. Those models are essentially based on the assumption of fixed wing flight for insects that might not hold.
Even a completely different Reynolds number type of.
Yeah,
That's what I'm wondering.
Yeah. So we think these are probably more valid for larger vertebrates than flying insects. I've talked with Florian Maurez at Wageningen University, who studies the biomechanics of flight. We're kind of interested in seeing where flying insects fit into this picture. So just based on these scaling relationships, it turns out that for terrestrial predator-prey interactions, they fall right on 1. So that it's just an even match. So essentially this model predicts that if predators are faster than average, they should have an advantage. If they're slower than average, the prey should have an advantage, and vice versa for the trait. So it's basically an even match, and small differences in trait values can tip the scales towards prey or predator. In aerial environments, predators are predicted to have a small advantage over prey. So on average, we should expect to see predators being able to capture their prey. But then if we have moderately faster or more maneuverable prey, that can shift the balance towards them. And then in the aquatic domain, the model predicts a substantial advantage for predators over prey. So prey would have to be many, many times more maneuverable or faster for them to be able to successfully execute this turning gambit and outflank their predators.
I mean, going back to this 2D, 3D problem, prediction is harder in the 3D text, right? Because
Yeah.
you have more degrees of
Yeah.
freedom. So
Yeah, so we're starting like with the simplest possible there will be like more biology and complexity as we progress.
Is there anything related to the rate of the masses, like for the aquatic, they're really much more than this sort of figure, or
So, sorry?
the rate within the mass of the
The rate, I think at least they're largely comparable. The predator prey, I don't have the figure with me here, but the ranges for aquatic and terrestrial are more or less comparable. There's a smaller range of body sizes in our aerial data sets because it's just the differences in size between like hawks and their prey tend to be not as large. But this is mostly driven, this pattern is mostly driven by the scaling of the traits more than the differences in body sizes across domains. Yeah.
To what extent is the hunting strategy of birds of prey can be classified as a pursuit? I mean, small birds can just easily get away from large raptors. I mean, they even can pick large raptors when he's come close to their nest.
Mm-hmm.
So I think generally how large bird of prey attack small birds just by flying very fast in a straight line as a sort of crashing into
stooping. Yeah.
Yeah.
So stooping happens, but there's also many examples of birds actually chasing prey. You can find YouTube videos where you actually see something that almost looks exactly like the turning gambit play out in real time as the prey does this looping maneuver and the predator tries to track but can't. So you see there, yeah, it can be challenging to make general statements about predation because animals are variable. There's different strategies, but this pursuit strategy does exist for flying predators as well. So if predator-prey interactions are largely a biomechanical arms race, then our turning gambit theory is valid, then we should expect to see something like this relationship for capture success across the domains. It's an even match for terrestrial, so we would expect them to have the lowest capture success. And then predators become increasingly advantaged as we move from running to flying to swimming. Instead, we see the exact opposite pattern of this prediction, where it is roughly the capture success is roughly 50% in terrestrial environments, but then drops steeply as you move to aerial environments and drops even more when you move to aquatic environments. So that we kind of see the exact opposite pattern as we would expect. And so then you've already identified many things that are missing with this model. But the thing that I thought, the thing that first came to me that I thought was missing in this model is the fact that in this model, the predators respond instantaneously to the prey's maneuver, but we all have sensory motor delay. It all takes us time to process and act on sensory information. You might not be aware of this, but if you want to convince yourself, you can do this nice ruler test where someone holds a ruler, you put your fingers here, they let go without letting you know, and as soon as you notice it, you pinch your fingers together, and then you can solve for your sensory motor delay. In this case, the subject's sensory motor delay was about 186 milliseconds, which is quite typical for human visual sensory motor delays. Humans are really slow, so I compiled some data on sensory motor delays. It appears to be a function of size, so smaller animals have shorter sensory motor delays, and typically over the range that we're considering in our study can vary from as little as 20 milliseconds to up to 200 milliseconds. So it's not a lot of time, so it might be fair to ask, does this actually matter at all for predator-prey interactions? But what they mean is that these delays mean that actions taken by the predator from outdated sensory inputs. And to calculate just how outdated these inputs can be, we calculated how much the prey can rotate. So how much of this turning gambit turn can prey implement in the sensory motor delay of the predator. And here we see really big differences across domains, where in terrestrial and aerial environments, due to the relatively larger turning radii, prey can typically, on average, get about 10 to 40 degrees of their turn done in the predator's sensory motor delay, whereas in the aquatic regime, due to these really small turning radii, prey can do a full 180 degree turn, often much more, in the predator's sensory motor delay. So this means that sensory information can become very outdated very quickly, especially in aquatic systems. So what were the consequences of this delay? Well, in all three domains, once you include sensory motor delays, it shifts the advantage from predator to prey. So rather than being predicted to be captured in all contexts or an even match, the prediction shifts that all prey should be able to reach this safe zone. Although it's important to keep in mind that this model is modeling the predator and prey in point masses. And so whether they capture or miss is just doesn't account for the fact that predators don't need to be exactly on top of prey. They have claws or a mouth that can capture prey, out from their center of mass.
Does that also mean that the predators aren't, that prediction isn't in your model for the predators?
Prediction's not in this model. So basically it's the same model, except now when the prey begins its turn, the predator keeps going for its sensory motor delay, and then you start this circle turn with radius.
Right.
But you can also get for every adjustment, the predator also has the delay. We include both delays or only the delay of the prey? So
we only include the delay of the predator based on the argument that it's the prey initiates the maneuver.
Oh.
And in a certain respect, the behavior, because there's only one collision course, the predator keeps moving on its trajectory to intercept the prey. The prey can essentially predict the predator's behavior and account for its own sensory motor delay by just initiating their turn. There's like one sensory motor delay before they would have if they had no delay. So they can kind of build in their own sensory motor delay to their decision for timing, whereas the predator doesn't know exactly when the predator is going to turn, if it's going to turn left or if it's going to turn right, and it can only respond with this delay.
keep going back with 2D, 3D.
Yes.
But I guess the biomechanics are biased towards one dimension or one plane in maneuvering for aquatic animals, right? Because of the biomechanics of the fins and everything else, and the turns are easier. So that also plays a role, right? It's going to be easier to turn left and right than up and down.
Yeah, presumably it is easier to turn left and right than up and down.
And is that
Yeah.
consistent with all the predator-prey relationships? So they have the same, because in the flight, I guess it's less so, because you.
Yeah, flight, you have the complexities of gravity to deal with.
Yeah.
And do you have maybe come next? Do you have the phase portrait with the delay, like this curvature shows from the textbook? How it
Should have a same curve, but not for your new model.
Oh, so which like this?
yeah,
but for your model.
for your model.
Like this curve or which?
No, the
Oh.
one that you just passed. This,
Yeah,
This, yeah. Sorry, I should have put this, but essentially it looks the same, except now instead of the predator responding right away, the predator keeps moving straight for its the duration of its sensory motor delay, and then it follows that curve. So essentially everything looks the same except the predator goes straight for its sensory motor delay before doing the same curve it would have done. It didn't have a sensory motor delay.
That gives more room for the predator.
That head start essentially allows the predator to always reach the safe zone with all the simplifying assumptions of this model in all three domains. How big of a miss distance that allows them then still depends on the other parameters of the model.
Does that mean that the prey is really much more unpredictable? Because I'm still stuck on this prediction.
Yeah.
Right? Like tennis players predict.
Yes.
They can't respond.
Yeah.
So the predator has to evolve to predict.
Yeah.
But there's an arms race for that too.
Yeah.
So that somehow the prey is more unpredictable. We
won't get to predators predicting things in the middle part of the talk, but there are some things that are just fundamentally unpredictable, right? Does the prey go left or right? Each of those has equal performance advantages for the prey, but the predator has to essentially, it could guess, but it can't accurately predict which direction, at least in an open environment where each option is equally good. We do have some like anecdotal evidence in our data set that eventually predators actually might try to just do the goalkeeper move and guess left or right, but I don't know if it's enough examples of that to make a claim.
And at least anecdotal evidence that rabbits, when they are chased, really do a random switching left and right.
Yeah.
Because apparently they're not actively aware themselves of where they go, and it's just sort of instinctively they do left, right, and if perspective left, right is apparently quite a well thought out random sequence.
Yeah, I mean, we also when we get to our escape data, we also see basically like symmetric choice between going left and right during pursuit.
I guess so.
So-
but they didn't keep, chasing it, so it's a bit. Animals are going to be harmed. Yeah.
One other consequence of introducing this delay is we found that it changed the sensitivity of predator-prey interactions to the biomechanical traits themselves. So the one I'm going to focus on here is this changing maneuverability, or changing the minimum turning radius. So like we would expect, if we take all the predator-prey pairs in the terrestrial and aerial environments, and we make the prey less maneuverable, so we're decreasing their maneuverability, and then we look at the miss distance they're able to generate, how big of a distance they're able to evade the predator by. We see that they quickly, a rapid drop in their performance as they become less maneuverable. So if they have to turn with larger radii, they have a large reduction in their fitness or performance. In contrast, we see the opposite pattern in aquatic environments where counterintuitively less maneuverable prey generate larger miss distances. And this is a little confusing until you consider the turning gambit model a little bit more in depth, where essentially this results from there being two maneuverability regimes in this model. We've characterized this low maneuverability regime where the prey are not able to complete a full 180 turn in the predator's sensory motor delay versus a high maneuverability regime where they can complete this 180-degree turn. So if prey are in this high maneuverability regime and they maneuver when the predator is at a distance of the predator's velocity times the predator's sensory motor delay, the predator arrives at the point that the prey initiated its maneuver just as the prey reaches this point up here, which is 2r away. So essentially they achieve the maximum possible miss distance allowed in this simple turning gambit framework. And because of that, they could, if they turn with it's so long as they can complete this turn in 180 degrees, they could turn with a larger turn radius and have an even larger separation. And so if we plot out for our different predator-prey pairs, the amount of turning that can happen in the predator's sensory motor delay, so this is on a log axis here, and then look at the scale, basically the observed miss distance versus the maximum miss distance for that turning radius. We see that most of the aquatic prey fall to the left of this WE times tau P, or omega P times tau P equaling pi, and have essentially they can do this 180-degree turn in the sensory motor delay of their predator, generating the maximum possible miss distance, whereas aquatic and terrestrial predator-prey pairs tend to fall to the left of this line and achieve submaximal evasion performance.
So the only thing that distinguishes in this plot the different types is the delay, or
so the delays are more or less similar across. At least we assume there's not a ton. All the data for delay comes from these data points, which are a mix of flying, running, and swimming animals. But obviously, you can see there's not really enough data here to detect differences. Although the scaling relationship there's not a lot of residual error around this relationship. So it is perhaps not different across domains. The main difference that's causing the difference in the value of omega E times tau P is the turning radius.
okay.
And because the omega P is the turning rate, so it depends on the speed and the turning radius. Flying and running animals are faster, so that actually gives them an advantage in terms of turning rate, but that's counteracted by their much lower, much higher turn radii. And then one final thing that we found is that we looked at how precise, so we can calculate whether prey are able to reach this safe zone, but there's one kind of free decision variable for the prey is at what distance do you initiate this maneuver? And what we wanted to know is essentially how precise do these maneuvers need to be timed for prey to be able to reach the escape condition as a function of the sensory motor delay of the predator. When the sensory motor delay is 0, prey are generally not able to escape, and so the window of allowable times that lead to escape is almost always 0. But then as we increase to a 50 millisecond sensory motor delay or 100, we see these non-zero escape windows. And the biggest pattern that I want you to focus on here is that in terrestrial and aquatic, terrestrial and aerial domains, these prey have much larger escape windows. So they don't need to time their maneuvers near as precisely as aquatic prey. And this has to do with the fact that the predators are also highly maneuverable, which essentially gives the prey just a very short window to execute this turn and enter the safe zone.
One thing I was thinking about is you assume that only the motor delays, like from the start to the kind of pursuit, but I guess also field of view has a big role to play, right? And some of the prey have eyes on the sides of the heads of
Yeah.
predators and something. So it's also the awareness of when the pursuit starts.
Yeah.
Is going to be a big factor.
Yeah, so this is, I mean, this model essentially, the initial conditions are already like towards the terminal stages of a pursuit where they're already on a collision course. It's easy for the prey to get to this initial condition. All you have to do is run or swim or fly away from your predator, and then you end up in a tail chase.
Do you know how many of those things happen where, the attempt and the pursuit just dies out and some continue?
I imagine that, so in our data set, which we'll get to a little bit later, prey often don't have to maneuver because they're able to reach a refuge before the predator before the predator can get close enough that the prey would need to do an evasive maneuver. But it probably varies. In other systems, it might be an endurance contest too, like a cheetah chasing an impala gets exhausted before it can catch up to the prey. So there's lots of like interesting complexities that we're overlooking here. So the conclusions from this allometry of pursuit analysis is that sensory motor delays kind of profoundly alter the geometry of the turning gambit model by giving prey a head start in their maneuver, and sometimes a very significant head start over their predators, especially in aquatic environments. And really, aquatic environments kind of pop out as being different from terrestrial and aerial pursuit in some interesting ways. One, they're in this high maneuverability regime where counterintuitively, prey are so maneuverable that further increases in maneuverability offer no advantage, and they can actually do better sometimes by turning at less their minimum turning radius. And also we have this issue of timing. So for this model predicts that for prey to be able to successfully evade their predators, they need to be really good at timing. One other thing that this model completely ignores is that essentially the turning gambit is only assessing if interception by the predator is biomechanically feasible. That is, if we look at all the possible paths, this shaded area represents all the possible courses of the predator, and if any one of them is capable of preventing the prey from entering the safe zone, it counts as a capture. But obviously, like in real life, you actually have to pick a trajectory, and you have to guide your movement from millisecond to millisecond using sensory information about the relative position of the prey. And if we keep in mind in aquatic environments, these delayed sensory inputs can become very outdated due to the turning capacity of prey. This should pose a problem just for generating an interception path to prey with very outdated information. So the prey could be swimming in the opposite direction that you currently are perceiving it swimming. And so we wanted to kind of move out of this geometrical framework into more dynamic models of pursuit that actually account for the fact that predators need rules or algorithms to guide their motion on a millisecond by millisecond basis to capture their prey. But to do this, we need a model. We need to make some assumptions about how predators actually do this. The nice thing for us is that this has kind of become a little niche subject for many behavioral neuroscientists who have started to actually look at, well, how do predators actually construct these interception paths to intercept maneuvering or moving prey? And surprisingly, across many different predators, researchers have found that animals or predators appear to use a form of reactive feedback control to intercept their prey. And specifically, one instance of feedback control referred to as proportional navigation. And so the idea of proportional navigation is pretty simple. It's based on the idea that if you're on a collision course with a target, the line of sight pointing from you to your target with respect to some external reference frame doesn't change. And so if your line of sight to your target is staying constant and you're closing in on the prey, that means you're on a collision course. And so you can turn that into that kind of geometrical fact of collision into a control rule by if the line of sight is changing, that means you're not on a collision course. But if you turn to counteract that change in the line of sight rate, then you can get yourself by iteratively turning in proportion to that the line of sight rate, you can cause it to go to 0 and then get back on a collision course, assuming the prey doesn't change its direction. And so you get a really simple model here where essentially the turning rate of the predator is proportional to this change in the line of sight rate, and the constant of proportionality is this k, which is like a steering gain. So like how a given change in the line of sight rate translates to a given turning rate. Higher gains, you get more responsiveness to a given change in line of sight rate. And importantly, we're also accounting for the fact here, we have this tau to account for the fact that predators don't have access to the current line of sight to the prey. They only have access to this delayed line of sight. And so what we wanted to do with this model is then kind of redo the turning gambit analysis, but focusing in on the aquatic regime where you get these like interesting problems of timing and control. So again, we wanted to know how the traits of predators and prey influence escape performance and the types of maneuvers that are more effective against reactive predators. We also go beyond like that simple, just prey stay on this turning radius or just follow this circle turning. And instead, we allow them to break out of this this minimum turn radius turn at some angle and continue on in that direction. So this is already beginning to look a little bit more maybe like some of these rapid turns when being chased by a hawk or a fox. And so we want to know, how prey timing and direction influence the outcome of predator-prey interactions. And importantly, we parameterize this model with aquatic maneuverability and speed traits. So what we've found is that the model is it's a little bit more complex now than this turning gambit model. It's you have nonlinear differential equations. There's a delay, but in spite of that complexity, what we found is that at least when predators are chasing their prey from behind and then prey make maneuver, the capture performance is this simple function of one predator trait, its sensory motor delay, and one prey trait, its speed. So essentially it's determined by the distance the prey can travel in the sensory motor delay of the predator. This plot is showing we changed the predator sensory motor delay for different prey speeds. So like the baseline rate based off of the scalings for speed that we found in aquatic systems, and then looking at if prey were 50% slower or 50% faster. And you can rescale all these lines, and you just see that miss distance is proportional to is equal to the product of the predator delay and the prey speed. And importantly, this model, although different from our turning gambit model, kind of reinforces this prediction that if it wasn't for sensory motor delays in aquatic systems, prey shouldn't be able to evade their predators.
Sorry, are these dots data? Or?
These are these are now simulation the average of simulation. So this is all model output. We model a given prey maneuver. We do many instances of the prey interception responses with randomly drawn speed and maneuverability traits from the distribution of observed speed and maneuverabilities. We also draw this gain parameter, so how sensitive the predators turn. Yes.
Would your ideas predict that predators generally have a smaller sensory motor delay than prey? Because that's really
I think so. Yeah, and
test that?
You could, yeah. So unfortunately, it's not a trait that has gotten a lot of interest in ecology. It's in and almost, I mean, it has gotten a bit of attention in neuroscience, but maybe not. The functional significance of sensory motor delays, I find, has been overlooked, at least in this field. We do find in the end, we find for our predator much lower sensory motor delay. Like a sensory motor delay is about half of what we would expect given its size from the scaling relationship I showed earlier. So it's possible. So you can measure this it would be a cool trait to have more data for.
Why is that half?
So we measured the sensory motor delay of our predator in our field work. So we looked at the delay between the prey maneuver and the predator beginning its response. And we found a sensory motor delay, I think, of about 35 milliseconds, which for the predator is also approximately a kilogram. We would predict a sensory motor delay of about 80 or 90 milliseconds for that predator.
Sorry, what are the exact equations of the model? Do you have them there?
I don't, I don't have the exact, essentially, this is the equation for the predator. The prey moves in a straight line until the predator is within some distance or some time to collision, and then it does this minimum turn radius turn until it gets to its ultimate turning direction, like here. And then we just calculate the closest the predator got to the prey across many iterations of this, drawing the parameter values from the distribution. And so it depends on delay and prey speed. It was also interesting the things that it didn't depend on. So it doesn't depend on, assuming the predator is faster than the prey, it's independent of predator speed. And also kind of confirming some of the intuition from the turning gambit model, also in this slightly more complex model, the maneuverability of both predator and prey don't influence the outcome in this high maneuverability regime. For the next thing I wanted to look at was the actual behaviors of the predator and prey. So for timing, the way we thought of this is when a predator's on closing in on the prey, this time to collision is going down. And the way we modeled the timing is that prey have some time to collision threshold, that when the predator is, for example, 100 milliseconds from collision, the prey implements their maneuver. And then we can look at, if we vary this time to collision threshold, how does that influence the escape performance? We see this hump shape relationship where if they wait until just before collision, obviously they can't generate a miss distance because they effectively didn't maneuver. And then maneuvering earlier and earlier, we get a larger miss distance until eventually it starts to go down again, essentially where these too early of a time to maneuver allows the predator to adapt its course. So it's kind of this trade-off between you maneuver early. If you maneuver earlier, you get further off the collision course. But if you move too late, you can't get far enough off the collision course. If you maneuver too early, the predator can respond. And then where this peak lies and is influenced by the sensory motor delay of the predator. So if the predator has a longer sensory motor delay, you can maneuver earlier and the predator's not have enough time to adapt its course to your maneuver. So with this proportional navigation model, we typically find that these optimal times to maneuver is about 2 times the sensory motor delay. And then for escape angles, I'll just talk about briefly. We didn't see as the escape angle, the direction that the fish ultimately flees to, the influence of that wasn't as important for the outcome, for the escape performance, as effectively any escape angle off the collision course was almost equally effective, but the very best escape angle is the one that maximized escape performance tended to go back in the direction the predators approaching you from. And this, I think you can start to see why the predator's speed doesn't matter, because if the predator's faster, it's closing in faster, but it also has less time to adapt to your turn because the closing speed is much higher. One thing that maybe you'd wonder is, well, so we have this gain parameter in this model, which determines the sensitivity of how quickly or how responsive are predators to a given change in the line of sight rate. If they're not capturing the prey at a given gain, can we just turn the gain up and the predators become more responsive and then intercept the prey? It turns out with this delay that doesn't work. And so this is showing the predator trajectory at different values of gain. We see at low gains under responsive, we crank the gain up to 2, a little bit more response, still not responsive enough. And then at a gain of 3, we see this loss of stability where due to the delay in this system, predators can actually end up swimming in the opposite direction if the gain is too high. So this would be like analogous to if you're driving on a highway and lose control of your car on a slippery road and are turning back and forth, or you're in a hotel shower and trying to get the temperature right, and you oscillate back and forth between scalding hot and freezing cold water. So this leads to some predictions. So if predators use proportional navigation, they should be influenced by this trade-off between responsiveness and stability. And if prey time their maneuvers well and maneuver quickly, they should be forced to either react too slowly or lose control against these timed maneuvers. And this should lead to some testable predictions about when predators can or cannot capture their prey. And so to test this, we came up with this virtual predation experiment where we project a little black dot on the top of a flume. And these rainbow trout in our study really they drift feed naturally in their environment. So they're used to preying upon things floating down the river. And they also are very good at it, very good at drift feed. The nice thing about this experiment is because we're tracking the fish during the experiment from below, we know where it is. We could actually program the maneuvers to happen just at a point that would kind of induce this trade-off between responsiveness and stability, essentially to see if we can, this model, these trajectories were designed effectively to break proportional navigation. We wanted to see if it would also break this fish or if they would somehow cope with this. So what we did is for each of our trajectories, so here's the fish, this is the virtual dot, these black points are just showing its position over time. You can see in this trial, the fish does a good job of intercepting this gray target here. We see the same thing in the plot below. So the fish were really good at intercepting these targets. We were not able to recreate the behavior of the predators by integrating this proportional navigation model from the point of maneuver. So we see this same trade-off between stability and responsiveness, where at low gains, the model predators under responsive. At high gains, it becomes more responsive early on, but then we see this loss of stability where it's often swimming the wrong direction. And you can see the same thing in the example below. So essentially for no value of gain, either low or high, were we able to recreate the behavior of predators in these experiments. The actual predators also did a much better job of capturing these virtual targets. So if we look at the minimum distance between the real fish and the target versus our model fish and the target, the real fish had much lower miss distances than this delay and compensated proportional navigation model. And so we thought, yeah, maybe the animals are compensating for these delays somehow by forecasting. And the reason we started to think about forecasting is that we noticed that fish were more sensitive to the target motion immediately following maneuvers than we expected from this proportional navigation model. So if you remember, proportional navigation basically assumes that you turn at a rate proportional to the line of sight rate. So if you plot the line of sight rate on the x-axis and the turning rate on the y-axis, the slope of this line is essentially the turning gain. What proportional navigation assumes that there's this one constant value of the gain that's the same over the entire trajectory. But when we fit this, when we look at this, the regression of the relationship between line of sight rate and turning rate at different points in time following the maneuver. So from right after the maneuver up to 100 milliseconds after the maneuver, the slope of this line, or the apparent gain in the proportional navigation model, starts off high and then decreases over time. And we thought this might be, rather than just the interception, its role of itself of some time-varying gain, we thought this might imply that fish were predicting, because if you think about what a fish perceives just after the target has changed directions, the new position of the target has just changed a little bit from its original course. But if you extrapolate that through your sensory motor delay, that leads to actually a big change in the expected position of the target from one step to the next. And so we evaluated a couple different models to try to incorporate this forecasting into a feedback control model, where instead of responding to delayed sensory inputs, what we found is the only model that could reproduce the behavior and capture success of fish in our experiments was included an internal model of self-motion, essentially to predict the consequences of your recent motor commands on your relative position to your target. So essentially predicting how your tail beats have moved you closer to your target. And also a simple linear forecast of target motion. You assume that the target keeps moving in the directions that you last perceived it moving, and you just extrapolate that forward one sensory motor delay. And then you apply feedback control, the same type of feedback control as in proportional navigation, but to these predicted rather than delayed sensory inputs. And when we do that, we see this model that combines forecasting and feedback can capture the observed capture success performance of our experimental fish, but it also can predict quite accurately the trajectories we observed in our fish on a trial-by-trial basis. Importantly, this whole model still just has one fitted free parameter for the entire data set, which includes, I think, like around 100 or so trials. So lots of data, one parameter, and we're able to make pretty accurate predictions about the behavior of the fish on a trial-by-trial basis. So it turns out, trying to understand why this model improves capture success performance. Essentially, proportional navigation works through iterating through this sensory motor loop where you see a change in the trajectory of the target that causes, after some delay, you respond. Then you see the consequences of your response on your relative position to the prey, which allows you to fine-tune your turning until you are on an interception course. So it takes one sensory motor. So if we think about what happens during a maneuver, it takes one sensory motor delay before a predator begins to respond. But importantly, it takes another sensory motor delay before the predator gets sensory inputs on how its own response is feeding back and whether it's sufficient or insufficient to make it bring it to a collision course. And that's important because it's this feedback that's required for the predator to actually get on a collision course. Otherwise, it's just very sensitive to the value of gain. It could be under-responsive or over-responsive.
Is there any kind of optimization to minimize time to collision here? Because there's many paths that could lead to collision, right? But there's some that are short and further paths.
Oh yeah, like if you're not starting with like a specific model and you're just looking at like what's the optimal.
What is the assumption that the predators can do?
The assumption is that predators are able to predict the consequences of their own motion and forecast the current trajectory of the prey forward through their sensory motor.
Depending on how far they are away, what the speed difference is, I can say there's many options I can intercept. Further along, or earlier. Are they trying to make it the
No, this is still essentially just following something very analogous to feedback control. Except on the predicted sensory inputs rather than the delayed inputs. So it's very similar to proportional navigation, but instead of using the delayed inputs, use the predicted sensory inputs you would receive if you didn't have a delay. So essentially this internal model of self-motion is important because you shortcut this second delay, and immediately once you begin to respond to the prey's maneuver, you're already predicting how that's changing your how close you are to being back on a collision course. And the consequence for prey anyways, of predators that predict is that even though they already had to they had to time their maneuvers precisely in aquatic systems, when their predators forecast, they need to time them even more precisely because predators can much more quickly reestablish a collision course following a maneuver against just a feedback control model. If they waited, for example, 2 sensory motor delays to collision to initiate their maneuver, they would be lead to these relatively large miss distances, whereas for a predator that forecasts, they can already compensate, they can already reestablish a collision course if they have roughly like 80 or 90 milliseconds. So against forecasting predators, you actually have to wait even longer till just before collision, and that means you can get less far off the collision course, and that limits your evasion performance. So essentially, if your predator forecasts, you're in a tougher situation for a prey. So the prediction is actually, so this last analysis assumes that fish have this fixed time to collision threshold. One thing we're interested in is that actually the optimal thing to have is a fixed time to collision, or does it depend? Yes.
What is brinkmanship phenomenon?
Sorry, I think I used to, so brinkmanship phenomenon is just like waiting until the very last, you basically have to wait until just the last minute to implement your maneuver. Whereas you might think, yeah, you would want to maneuver as early as possible to get out of the way of the predator. When your predators respond to what you do, you actually want to kind of wait until just the last minute, just to the brink. As I said, this just assumes a constant time to collision threshold. It turns out that the optimal time to collision threshold depends on how quickly the predator is closing in on you. So you get something, so this is showing the closing velocity of the predator, so the difference in speeds. And then this is showing the time to collision, and each of these tiles here are colored in as a function of the miss distance, where this bright band represents this kind of optimal maneuver timing. And what we see is that if the predator is closing in slower, you want to maneuver earlier with a larger time to collision. This is just the proportional navigation model. So if we incorporate forecasting, the shape looks qualitatively the same, but everything is shifted down. You need to wait a little. You should always maneuver a little bit later compared to a model without forecasting. So low closing speeds, prey should maneuver earlier at a higher time to collision, and at all closing speeds, prey should maneuver later against forecasting predators, which leads to smaller miss distances. So sensory motor delays, if they're not compensated for, can lead to a loss of stability against fast maneuvering prey, and the predators in our study appear to compensate for these delays. And that should make evasion really challenging for prey in aquatic systems, because they have these like maneuver windows on the tens of milliseconds if they're to escape, which is kind of hard to reconcile with the fact that I've already shown you this plot where capture success is about 10% on average in aquatic systems. So how are prey actually able to evade predators that are even forecasting to overcome their own sensory motor delays? And to answer this question, we went to Curacao to actually try to film predator-prey interactions on coral reefs. Again, this is Lars Koopmans, who led most of this research, and in spite of the fact that he's coming from a physics background, turned out to be an excellent field biologist, although perhaps a reluctant field biologist. So we had to film a lot to get these videos. So predation is ubiquitous, but it turns out it's very hard to capture on camera. So we filmed for 1,500 hours in Curacao to try to get some of the attacks. But if you film for long enough, you get really cool videos like this. We see this barjack chasing a brown chromis, the focal prey species of our study, and the prey doing a series of evasive maneuvers and ultimately avoiding capture. So this is dramatically slowed down just to give you an impression of what this looks like in real time. It's basically a flash. So the amazing thing to us was in 97% of the attacks that we observed, the prey get away. In spite of the predator is much faster, but the prey get away almost all the time. How is this possible? Well, we already have some intuition from all the theory that we worked out. Is one, we know they're in water, water's dense, so they can turn very rapidly. We also know predators have sensory motor delays. And because given typical sensory motor delays and turning rates in aquatic environments, prey should be able to do most or all of their maneuver before the predator can even respond. But as we saw in the last model, for predators that forecast this, all of this only will work if prey are really good at timing their maneuvers, like to the tens of milliseconds.
One thing I thought Mike asked, the maneuver in water can be any dimension.
Yes.
The maneuver in the flat plane can be also predicted by the prey, no?
So they can in theory move in any direction. Typically, like when we look at these maneuvers, you can describe most of the variation in position of just with a plane.
I see.
It's strange why that is, right? So I would assume some prey just adapt to be able to. I'm thinking of aeroplanes, right?
Yeah.
In dogfights.
Yeah.
It's the same kind of thing.
You only speakers, you play again, see the
Penguins and
maneuver
penguins.
was.
Yeah.
Okay.
That's really 3D, at least from the we've seen, right?
So the penguins are just.
Yeah.
Okay. And do you measure something about the bias in these? So whether it's biased towards this kind of flat plane of motion rather than, and whether that affects the balance rate relationship.
Did we?
Well, most of it is like parallel to the seafloor.
Yeah.
But I think there's also just how they move through the reef and how they.
Also, biomechanically, also what the quicker it's and less than probably going up, right?
Yeah, but I think when they go up, it's they first turn sideways and
They
then
get more parallel.
yeah.
But I guess. But I was thinking about squids.
Yeah.
They are much more able to kind of move in 3 dimensions, I would guess, right?
And
Yeah, but they also obey different biomechanics.
Yeah.
it would
Fish
be
like this.
quasi 2D because the in escape would just be epsilon above the plane, and I don't know how they quantify that. That's a more degree of freedom than terrestrial.
Yeah. I think, I mean, in some cases, these maneuvers are 3D, but I think, and the models that we use for the predators are also in 3 dimensions, but so far we find that these like 2D, these 2D models also capture most of the dynamics going on during these maneuvers.
One of the questions are about this anticipation of the prey to the predators. So, just in time.
Yeah.
Is it always the case that the prey can see the predator? Or are they opting for random stochastic movement that they don't even?
We think, well, as we'll get to this a little bit later, but given that how precisely these maneuvers are timed, they must be able to sense the predators somehow. The weird thing though is that they're mostly being chased from directly behind, and their eyes are on the side, but they do have blind spots.
Yeah.
And so we don't actually know yet how they're telling that the predator is close. It could be they feel the predator, or as they beat their tails, their heads going back and forth, and they get just snapshots with each tail beat to see them. But they must. It's definitely not random.
Okay.
They just have a hunch. Yeah.
I was thinking of a strategy for the prey. If it moves erratically enough, and then you can go over the sensory motor threshold of the predator, and you can never predict. That's why I was walking about this time to collision.
Yeah.
The predator, has to kind of make a prediction path which allows it to intercept.
Yeah.
It's moving so erratically, you can never predict. And whether it learns that, right?
Yeah.
The prey is moving so quickly,
Yeah.
and I can't predict. So.
Yeah.
And maybe this relates to this goalkeeper movement that you were talking about. Okay, I give up. I'll just go and see what.
Yeah, but then if you're moving erratically, when the predator is not close to you, then the predator gets to catch up to you really quickly.
Okay.
And so actually, we look at lots of different trajectories. So basically, for prey to be able to escape, 3 things I think need to happen. 1, prey need to be able to make sharp turns. Predators need to respond with delay, and prey need to have really good timing. So we looked at each of these. So this is just showing some of these trajectories. The predator is in red, the prey is in black. So you often see something that kind of looks like the assumptions in our model, where they mostly move in roughly straight lines until you get to a maneuver, and then you see these really rapid, tight turns, often that look like these little looping maneuvers. And we found, on average, the turn radius of prey during these maneuvers is approximately 4 centimeters. So like again, these are really tight. This is kind of in line with what we would expect, actually a little bit greater than what we would expect to see based on their minimum turning capability. So these fish are about 5 to 6 centimeters on average. And in aquatic environments, prey or animals can typically turn in about like one fifth of their body length. So they're turning at about 2 to 3 times greater their minimum turning radius, but that's also kind of in line with the turning gambit results we showed.
So if I look at these lines, it looks like that the red lines, so the predators, make way sharper corners than the prey. I mean, especially if you look at line 2 and 3, I mean, you get these very sharp angles.
Yeah, it's hard to, I mean, it's kind of hard to, that's the curse of 3D is whether it looks sharp or not can be really influenced by which direction you're viewing it. And so I think in general, the turning radii of the predators is larger than the turning radii of the prey in our study.
So this is mainly an effect of just a projection.
Yeah, I think so.
Happening.
Yeah.
Does the fish perceive alteration of the water around, like a pressure or sound created by the predator?
Yeah, so in laboratory studies, you can turn off the lights and take a model predator and push it towards the prey, and they'll escape. The difference, though, is these are like done with zebrafish larvae at speeds, less than like a couple centimeters per second, while the zebrafish larvae is essentially immobile before they're just kind of randomly not swimming very quickly and often not moving around. In this case, they would have to be able to detect the pressure of the predator coming behind them while they're swimming at 50 body lengths per second, which it just seems like there's the turbulence involved is going to be incredibly complex. So I think they might, but I have no idea how or how difficult of a task that is to pick out the signal of a predator approaching you from behind when you're in this regime swimming 50 body lengths per second. So the other thing is that predators need to respond with delay. This is just showing one example video where we see the prey maneuver here, and then the predator doesn't respond until well after the prey has made this maneuver. And when we do this for many different attacks and look at the delay between the prey's maneuver timing and the predator's response, we find on average these predators have a sensory motor delay of about 35 milliseconds, which is actually less than I was expecting this to be more in the 60, 70, 80 range based on their body size.
The delay, you mean by the visual cortex, or I don't know how fish are, the delay, the perception they have in the body or in the visual cortex?
Presumably it's mostly, I would guess it's mostly, so if you just look at like stretch reflex delays, which it doesn't involve processing a complex visual signal, those delays are much shorter. So presumably for visual delays, a lot of it is the actual computation of breaking down this complex input into useful features to make decisions with, like time to collision, for example. So visual sensory motor delays tend to be longer than auditory sensory motor delays, which tend to be larger than like touch sensory motor delays. So because prey can turn rapidly and predators respond with delay, prey can, in theory, maneuver behind the predator before the predator responds. And we see that here. So these are showing the azimuthal angle of the prey to the predator just at the time of maneuver as a function of time. And by the time we get to the predator's sensory motor delay, essentially all the prey that were initially in front of the predator end up quickly behind the predator. So, and before the predator can respond. But for that result to be true, we needed the maneuvers to be timed precisely, because if they're timed too early, the predator can respond. If they're timed too late, they don't get off the collision course. And so we wanted to look at how precisely these maneuvers are timed. So again, this is just going back to that optimal timing of collision model. This is for the delay and compensated model, so proportional navigation. And we can compare this. So if the prey are behaving optimally against a predator using feedback control, we would expect them to be on this band. We tend to see that the observed maneuvers, these red points, occur later than expected against a reactive feedback-only predator. But they're almost perfectly in line with the predictions you'd expect to see against a predator that's combining forecasting with feedback. So one thing to notice here is this band is very thin, and almost all of the data, almost all of our observations fall within this narrow band, suggesting that these prey are able to time their maneuvers very precisely. Another thing it says to me is I think it speaks potentially to the generality of these behaviors, because we identified this model in the first place studying rainbow trout in Florida to generate these predictions about how prey should time their maneuvers. And then we find this exact timing pattern in the coral reefs of Curacao with completely different species. What happens when they don't time their maneuvers correctly? So we don't have many, obviously there aren't many data points that aren't right on this band. Here's an example of one. So it's interesting to think of what happened here. This was kind of a unique case where this prey here was being chased by two predators. And so as you'll see, this will play a couple times, the prey does a maneuver. It seems to get away from the first predator, but then into the mouth of the second predator. And then if we can use this, we can calculate what the closing velocity for each of these predators. So this is for the first predator. This maneuver was timed right in this band, and the prey appears to get away from that predator. But because the second predator was further behind, traveling a little bit slower, it was too early with respect to the second predator, and this maneuver is poorly timed, and ultimately the prey was captured. This also suggests some benefits of group hunting because it's very difficult to time your maneuver. Because timing needs to be so precise, it's hard to be precisely timed for two different predators. So aquatic prey are able to evade because the density of water allows for rapid turning. Predators respond with delay, and prey time their maneuvers with precision, at least in our study. So we found this in our study. It's unclear if that holds generally, but given the empirical observations of very low capture success rates in aquatic systems, it suggests that these might be general factors reducing capture success in aquatic systems. You'll also notice there are some points here that are higher, so it's not always very low. One other thing that we didn't really talk about in our study is the existence of coral refugia that prey can swim to, and once they get in the coral, the predator gives up chase. So the result of that is that prey only have to do, in our study, 1 or 2, maybe 3 maneuvers before they're able to reach a coral refuge, and then that terminates the chase and they're safe. In other environments, that might not be the case. So here's a cool video of a dolphin chasing a fish. This video has already been going on this chase has been going on already for a couple of minutes. And what you'll see is this fish keeps doing evasive maneuvers to get away from the dolphin. I think it did 20 or so in this pursuit, but eventually, because it has nowhere to go, it has to keep doing these evasive maneuvers. Presumably, at some point, it gets exhausted, and the larger dolphin can eventually capture it after it slows down. And I think this happens shortly after this. So it just highlights, in this case, the importance of having some structure like coral reefs to reducing capture success rates. Yeah, this goes on. There we go. Who's got it?
Why doesn't the dolphin get exhausted first?
Presumably, so they're using anaerobic fuels for these high-speed pursuit, which in general, I think there's no scaling relationship between the density of anaerobic fuels and body size. So larger animals have just more absolute anaerobic fuels than smaller animals. And the scaling of energetic costs for swimming is typically proportional to like mass to the 2/3 power. So like surface area rather than it's surface area for the energetic output, its volume for the energy store capacity. And so you would expect in general smaller animals to get exhausted first in swimming.
Yeah, and anaerobic vision.
Yeah. And generally bigger animals tend to have higher maximum speeds at their aerobic limit too. So they don't need to dip into their anaerobic fuels as strongly as maybe a smaller animal does to reach these high speeds. So that's kind of the end of my talk. And just to conclude, what I think is really exciting about this niche field of predator-prey interactions is you have this really universal behavior where overall the rules are more or less the same. Predators need to get close to the prey need to get away. And you can think of predator-prey interactions as this very conserved evolutionary game. But to me, what makes it interesting is that the cast of players that play out this game vary so dramatically in the medium through which they move, their biomechanical traits, even their brains, their behaviors. And so I think it's a really nice behavior with very important evolutionary and ecological consequences for this comparative study. The conclusion from this talk is, while we've typically thought of predator-prey interactions as this biomechanical arms race, it actually turns out that a trait related to information processing, so sensory motor delays, actually is as important or more important than these biomechanical traits, especially in aquatic environments. We see that both predators and prey have tried to deal with these sensory motor delays. So predators appear to use forecasting to try to compensate for the negative consequences of these delays on their interception performance. And prey also seem to be able to time their maneuvers in a very precise way to exploit the sensory motor delay of the predator. And then the other thing is that, to me, what's exciting is that we have these relatively simple models like, this forecasting plus feedback model, or these models of evasion timing and performance that are able to predict kind of key aspects of the behavior of both predator and prey, which to me is a positive sign suggesting that we might be able to understand and predict some of this huge variation that we see in capture success across different predator-prey pairs, and also kind of help us by predicting that variation, better understand the evolutionary and ecological consequences of predation. So that's my talk. Thanks a lot for your time.
Thanks, Ben. I have listened to it before, but yeah. Yeah, any last couple of questions maybe, and then we go for lunch. Yeah.
And one sort of general question from the evolution perspective. Some organisms are of course both predators and prey.
Yeah.
So in terms of this arms race, whether it's sensory delays or biomechanical, are there any sort of conclusions about how organisms might adapt not only to better predators but also more effective invasive prey?
Yeah, that's not something I've thought about. From our results so far, it would suggest that the traits that are most strongly under natural selection actually might depend a lot, depending on which environment you're in. So in the aquatic domain, to the extent that animals can reduce their sensory motor delays, I think this theory should predict that would probably be one of the most dominant traits under selection, and that to the extent possible, predators particularly should try to reduce their sensory motor delays. Whereas in terrestrial environments, it's very, and aerial environments, things are very sensitive to the turning radii. So being more maneuverable becomes quite important. I'd have to think a little bit more about what the implications would be of being both a predator and prey.
Well, that looks so I was wondering, so in this third point, that the prey are able to evade predators by precisely timing.
Yeah.
But, so you talked about it, but I don't think you talked about the decision the prey makes is in which direction to move. So is there, from the data you have, can you infer something for how they decide what the maneuver is, or?
Yeah, that's a good question. That's a harder question because just characterizing the maneuver in a simple number is challenging due to the complexity of some of the maneuvers. Some of the maneuvers you see like a very simple loop, and then you can characterize it by the turning radii and the initial direction. Others you see more complex maneuvers where it's already, I think the prey it's not open loop anymore. The prey is responding to the initial changes and what the predator's already done. As far as the initial turning, it seems to be more or less random between going left and going right. We're interested in seeing how much can we learn from the trajectories, but it's a little bit harder than timing because you can't boil it down to like a number.
So the turning angle is a number in some
Yes.
sense. If you just approximate it by straight lines, and no loops, but just straight angles.
Yes. Yeah, then we have like a distribution of angles at different points in time. Yeah.
I really like the talk. I also learned a lot. Thanks. We usually have this discussion parallel prey on the population dynamical level.
Yeah.
And you bring us individual level. Do you think what you do can bring back to the population dynamic level, like that would affect your type of dynamics by knowing these details?
It could, yeah, in different ways. So one is just like the distribution of, so if you're interested in a food web, what is the distribution? How does the fact that prey can evade predators so well influence the distribution of attack rates in a food web with different predators and prey? So it's kind of influencing the distribution of the magnitude of interaction strengths in a food web, these behaviors. So I think it can do that. I think then there's also, does it actually change in just like a simple two species model? Does it actually change like the functional response between predators and prey? So there's been some work by my colleagues showing the fact that evasion success is often low, but then leads to behavioral changes on how available prey are for other predators. You can get all sorts of complicated and interesting positive, negative relationships between the density of two competing prey and a predator due to the changes in their kind of faster timescale behaviors. So I think we could also see something like that as well.
Thanks. So I have just one more question, just following up on Christian. So is there I know you have a rich data set. Are there plans to incorporate, other things like apart from sensory motor delay to look at other functions, like for instance, the angle of maneuverability?
Yeah, so I think
like looking forward, what are the things that you are, I don't know, with this huge data set that you're
yeah. One, it would be really interesting to look at other, so we've kind of gone in depth now for aquatic systems. I'd be really interested to see, can we work it out with this level of resolution for what's the really dominant trait in terrestrial interactions or aerial interactions, and how does that compare? Flying insects are also, I find, to be really interesting because I think they might also be in this high maneuverability regime. So there might be some kind of analogies, but or some connection between the dynamics we see for fish and also for flying insects as well.
Okay, if there are no more questions, let us thank the speaker.